I hope in the first 3 lectures we had some general picture of this 3-dimensional quantum invariance and 3D TQFTs in particular. Like we have 2 kind of main constructions, surgery and state sum, and then we have some relationship between them. That's I try to explain in more detail in the first 3 lectures. Today I will give first some recap, maybe just kind of a, if you are lost in the details of last 2 lectures, the surgery and state sum invariant, maybe I will give a kind of short 5-minute recap of what we have done in the first 3 lectures, and then go with the generalizations and perspectives. Like they're kind of similar meanings, maybe in some sense, maybe in other senses. They're very different things, but there are quite a bit of ongoing research in this field, and they're very interesting perspectives. Like it's like a branches of this story. Like the main story is like written Rashad and Vero, Barrett Westbury, and the connection between them. There's algebraic theory and there's a topological theory, manifold invariance. This is kind of a big picture, maybe overall, the core of the 3D TQFTs, that is in this classical sense, like these. And then there is these branches that, and then I'll try to explain some of them, not all. Okay, let's maybe do a recap first. Okay, the first lecture, maybe if I separate this part, I will like this and make edit and come back. Okay. The first lecture, what we have seen, it was all algebra. There was no topology at all, except examples that I provided definition of a TQFT shortly. Other than that, it was all preliminary algebra, like not, I mean, preliminary in the sense that understanding this 3D TQFTs and 3D invariants, 3D TQFT invariants. So what were they? Let's go. We started with categories and monoidal categories. And then we put like monoid categories are kind of a categorification of a monoid, like category with a product structure, associative up to coherent isomorphisms, and unital up to coherent isomorphism, which are kind of nicely generalized versions of monoid axioms. But with putting extra conditions and maybe structures, we provided new definitions, right? What we had? We had rigid monoidal categories. Roughly, what does that mean? It's a property of a category. Like every object, okay, admits both left and right. You okay? So this is like a condition. Every object admits both left and right. We don't choose. It's just it's just whether do they satisfy or not. It's kind of a condition that objects of a category and morphism satisfy or not altogether. We don't keep every object within, like, for example, this was not rigid, right? Category of k vector spaces and k linear maps. This is not uh, rigid because it has infinite dimensional vector spaces in it, which do not admit, in this category, which do not admit duals. So this is not rigid. Well, we had left rigid and right rigid, and rigid means both left and right. But it's just details. But if you put maybe finite dimensional vector spaces, then it's going to work. Every finite dimensional vector space admits it, but next to be pivotal, okay, pivotal monoid category has more information. It's kind of a structure, like every object, yes, it is rigid, but with plus additional duality data for each object. So every object is equipped with, there's a dual both left and right. There's another object which acts as a left dual and right dual. It satisfies the condition, but we fix this dual object. Right? Every object, the dual is chosen in the category vector space. Maybe choice of a dual, choice of a basis. Once we choose a basis, we can define duals by using the dual basis. So, okay. And next, what we have seen again, this was like the first one was like a property, second was like a structure, and now another property on a spherical monoidal category. So what does that mean? Okay, pivotal plus left and right traces agree. For any endomorphism, left and right traces agree. So what is, then I try to explain why it is called spherical. It's because until now we can define graphical calculus. We also define graphical calculus, Penrose calculus for one of the categories. With pivotal, with the fact that we have dual data for each dual, we fix a dual, we make it diagrams with arrows, our graphs with arrows. But now, these up to this point, what do we know? The thing that isomorphism or isotopic classes of this graphical calculus is equivalent to the diagrams, the corresponding, like when we take a diagram and associate a morphism in the category, this assigned morphism in the category is independent of the that isotopies that we do and some moves that we do in the category. Remember, just usual pulling and pushing, and these are all inverse. Now, when we do spherical, then these isotopies extends to isotopy of sphere. For endless or free end diagrams. So which means when we have a morphism, which is just endomorphism of a one, right? Which doesn't have an end. End means the source or a target. Source or a target of the corresponding morphism, if it is different, if it is not one, if it is just one, if it is not one, then we call it there is end. That's either source or target, or altogether they are different. But if it is endless, then the isotopy of this diagram, we can add this plus trace condition says we can do this pulling back the other way, and so isotopy extend all S2. Well, next we learn another structure again, like braiding and braided and symmetric or braided monoid categories. So in the category we have this braiding for every object, and then next we have symmetric monoid categories, which says when we do this again, this is equal to identity. Second computativity constraint. And other than those, we learned very important fusion categories, refusion and fusion categories. And next we learn when we have this braiding, we define right ribbon categories. That means we have left and right ribbons. Oops. Defined like this as a graphical calculus, and then they're equal. And plus, from those, we define modular tensor categories. So what is it? Modular tensor category is a Brane fusion category whose S matrix is non-trivial, and an S matrix for each simple object is given like ij, which are simple objects in the category. For each ij, this diagram gives an element of endomorphism of 1. But since underlying category is fusion, this is equal to k. So this is the number. So this gives the I row jth column entry of the S matrix. If the determinant of this matrix is non-zero, then we call this fusion category, braided fusion category is non-degenerate or equivalently modular tensor category. And for us in the topology, we had two important ones in all these collections. The one is modular tensor category, okay, and the other one is spherical fusion category. Okay, but in the second lecture, right? Maybe a little bit longer. The input, what we had as an input, modular tensor category. See, then for this and plus closed-oriented 3-manifold. Right? And next, what we do, choices, set of representatives of simple objects of C. This is I. We make this choice. And another choice is we make a choice that M equals to S3L. What does that mean? M is obtained from framed link surgery on a framed link. Surgery on a framed link in S3. Okay, this is always possible by Liparish-Volta's theorem, and then this is the link that we choose to represent M is a choice that we make. And this is not unique. This frame link is not unique, and they're all possible choices are kind of related by Kirby calculus, okay, Kirby moves. And specifically in this case, we don't use Kirby moves, but Van Roorke Kirby moves, which are equivalent but kind of simpler in this setting, in the quantum topology setting, in the formulation. And next, a quick step, like steps. Okay, operator invariant of L in with respect to category C, right? We kind of write this link to this frame link as a diagram on the plane with pluses and minus data, like with grading data, and then with respect to C, this is just a ribbon category correspondence, right? And then we get an operator invariant, and then we introduce colors. Sum those invariants over all colors, and color means assigning to each component of the link a simple object of the category, right? If you have n many components, there are n square, like, and if there are n, this is L1, L2, Ln, and then I as M, then how many colors we have? For each component, we have m to the n, m to the n many colors. Okay, so for computation purposes, it's better to write this equivalence as many as less, like quite a bit less components to do computations. That's for efficiency. And yes, and scale. scale according to fan. Oh yeah. Okay. Kirby moves. And understand invariance of these things under these moves that do not change the resulting. They change these moves that change the ribbon diagram of L, but does not change the resulting manifolds, right? Corresponding Kirby moves in this sense. So kind of a really physical way of doing this. Assigning colors is like assigning a state and summing all over with appropriate scaling, appropriate weights. In the third lecture, what we did, we used some approach where back then what was the input? Spherical fusion category. So it's taking longer than I expected, but in any ways, I don't have that much material in the rest of the thing, so it doesn't hurt to make an extended review of what we have done. Spherical fusion category, we picked C, right? And from this, and plus again, M oriented, and its boundary is empty, 3-manifold. We choose this, and then choice we make, and similarly, it's I simple representatives of simple objects in C, and plus, in this case, what did we use? We use kind of a triangulation, more like combinatorial approximation of M3 by simplices and the skeleton P of M. And the most basic skeleton comes from taking a triangulation and looking at its second skeleton. Just looking at the zero simplices, one simplicity, and second simplicity, it's going to be a scale. Whenever we pick a triangulation of such a manifold, first two simplices, collection of all of them is going to be a skeleton. So here's an example, which is better in the sense of simplicity than choice of a spine of a 3-manifold. Okay, we make these choices similarly, and then what were the steps? Okay. In this case, we again find operator, okay, assign colors to regions. Okay. So each region, each two simplex, which is oriented because skeleton means two simplices, their interiors, not boundary. The interior of two simplices, which we call regions, are oriented. Each of these regions are colored, or each coloring provides a simple object for each colors. We first color, and for each coloring, we kind of compute like operator invariant, right? Right. On two ways. Once we kind of find the dualities corresponding in the edges, taking different orientations, and also for every kind of vertex, we take a ball around it. We get a C-colored graph on the boundary of this ball. But the fact that category is fusion, right? This is invariant under the isotopies that we choose in the on the sphere, because this what we obtain on this sphere is precisely endless free and C-colored graph, which is just provides a number. But in this case, this operator invariant, in fact, provides a dual element on the corresponding products of vector spaces that are associated, given from the home set, like multiplicity modules. And then we evaluate at this dual object the co-evaluation element coming from the edges. duality in the edges. And we do this for any color, we get a number, and similarly, we sum, like we get this number, okay, sum over all colorings. So again, a coloring and this number is like a state, and then we sum over all such colorings, plus we need to do scaling. Scale according to the primary moves on skeletons. So this choice is not unique as well. Whenever we choose two skeletons of the same manifold, we know this theorem by Tribe and Realizia that these two skeletons are related by kind of ambient isotopy plus 4 invertible moves. And then what we need to do, like since we want to show independent of this choice of skeleton, we need to show whatever we need to scale this sum in a way that this is invariant under these 4 moves. Kind of similar steps, just looks like study different perspectives of getting this manifold. One is use a surgery, the other one is taking a manifold, and from the interior, it's getting combinatorial data from the skeleton. Well, at the end of the third lecture, what we did, we went to connection comparison theorem. Well, we have seen in the first lecture that Miguel says center of a non-zero dim spherical fusion category is modular tensor category. It's a modular category. That is we know. So, and then the natural question is, yes, we take here non-zero dim. Right? Dimension of the C is non-zero. Dimension of the category is non-zero. That its center is going to be modular category. So we take a C, that its center C is spherical fusion category with dimension non-zero dimension. Then by the theorem of Miguel, this is going to be modular tensor category. So what do we know? For this one, we can associate this TQFT, state sum TQFT, and for this one, we can associate surgery TQFT. And question is, how do they compare? And the point is, they're equal, isomorphic. These two TQFTs are isomorphic. So, and one may ask then this question, whether all modular tensor categories are center of some fusion categories, and the answer is no. That implies surgery TQFT in some sense, right? Is because there are more candidates to create this TQFT. If not all modular tensor categories comes from spherical fusion categories, that shows surgery TQFT is kind of stronger than say some TQFT, because there may be some invariants that cannot distinguish, like there may be some state sum constructions, state sum invariant of closed 3-manifold, which cannot distinguish two non-diffeomorphic closed 3-manifolds, but there may exist some modular tensor category, which is not a center of a sum fusion category, then such that the corresponding invariants can be distinguished. In this sense, surgery approach is stronger than the state sum approach. So this was kind of little bit longer review of all the 3 lectures that we have covered. Well, it was a little bit longer, but I hope if you get lost at some points in the details, this give you the big picture of the process. What are the inputs? What are the processes, and how do we get? Maybe you can make way better connection with physics than I do, and I don't know physics. And then this may help from the combining first 3 lectures. overall. And today I will review again a little bit what we have done last time, so that how do these things, from which perspective they generalize. Each of them kind of uses different perspective. The first one I'm going to cover is extended TQFTs. And in extended TQFTs, they are, well, again, I will make a comment, but I don't want to get ahead of myself. This is kind of physical. Well, again, somehow, maybe not the right, but kind of there's a locality principle in physics. They and maybe quantum field theory, which I don't know. But there's kind of that motivational perspective, which I don't know, but hopefully when I talk about the extended ones, I can say a little bit more. We can make better interpretations, whatever. Let's see. Now remember that functoriality of the symmetric monoidal functor at three-dimensional TQFT, what does that imply? Okay, we read cobordisms, which is a morphism in this category, right? V is a morphism from in COP3 from sigma 1 to sigma 2. Okay, but V in this sense, V is composition of V prime, V double prime. Right? When we choose a codimension 1 submanifold, like sigma 3, when we cut along codimension 1 submanifold appropriately, which is a surface, again, that's something singular, which is a smooth surface, when we cut along it, sigma 3, then we assume that we separate W into disjoint of two submanifolds. Okay. Then the composition in this category is precisely gluing along common boundaries. In this case, that means this statement. And then, so the functoriality of this functor, just functoriality, not even monoidality, says this quantum invariant, whatever it is between these states, these vector spaces, can be written as composition of this one and this one. So in particular, this says what? Maybe it is not always the case, but maybe purely this says that, okay, let's take a three manifold and then chop it into very, very simple pieces. Okay, make it very disk. Choose a two like sphere followed by something which is two-dimensional, like another simple thing, and then maybe the composition is, we write the manifold as composition of many things, but if each piece is very simple, okay, like some simple between surfaces of maybe S2s and torus and things, which may be done, maybe using JSJ decomposition, whatever. And then one can say, okay, if we understand this TQFT behavior in the simpler pieces, then we can understand overall by just taking composition of them in algebraically. So if we know, if we make this W primes, W prime and double prime many times, we do this cutting operation many times, so they are very simple. And then we understand associated invariants. Then whatever this numerical invariant maybe if it is closed, oops, if this is closed, there is no boundary. So if there is no boundary, then we have co-evaluation and some simpler morphism that we all understand what happens in them, and then we do evaluation at the end. Then this thing can be determined just with finite amount of data if the category is generated by composition of certain number of cobordisms. So this is kind of a computability approach. Like this functoriality property that this invariance, this quantum invariance behaving well under cooling says, okay, we can, like, this cutting is very useful in this sense. This cutting along coordination one. So if something is useful, and the mathematicians in general, they abuse it, like, because they want to make it even more useful. And what is the kind of the way to abuse this maybe is, and maybe it doesn't come to my mind, but in the second half of 19th century, 18th century, 20th century, and like there's developing another theory in algebra, like higher categories, 2 categories, 3 categories, and 4 categories, and then they're similar, and then one see the relationship between this, and that is cutting along higher codimensional manifolds. So what does that mean? We don't just cut codimension one submanifolds, like in this one direction, but we cut along codimension two, which has transversal. Okay, when we do this, we get instead of getting a surface, we get some surfaces with boundaries. Okay, like we cut along this cobordism W, we have the same cobordism still. We cut along this codimension one manifold, plus we cut along this another direction codimension one. Okay, not in the composition way when we look at in the R category, but kind of transversal another direction. In this space, this direction exists, and we can do this. But introducing this direction, uh, is amount to going from cob 3, okay, to some 2 category. Okay, this is one category. That means there's only kind of one way to compose the morphism. There's morphisms and they compose in just one direction. But in 2 category, there are one morphisms and 2 morphisms, and one can compose 2 morphisms either like vertically or horizontally. This is kind of the idea. So if cutting and pasting is very useful in the non-extended case, in this case, one immediately says, okay, then if we cut along transversal different directions, then we can get even more simpler data because manifolds are going to be lower dimensional, right? Because in this case, the intersection of these cuttings, what do we get? When we do this cutting and plus this cutting, the intersection is codimension 2 manifold. In this case, it's always going to be circle, right? Or bunch of circles when we cut through this. So and circle is way simpler than surfaces because their classification. For even higher dimension manifold, one cuts even more directional ways, and they get a kind of a more simpler manifolds. And it says if we understand what does this TQFT does in each pieces, right? And we get kind of simpler pieces because we get lower dimensional manifold. If we understand them better, then we can do this computation way better than what we did before. And for example, in this case, what happens, like we cut through this 3 parts and then this one, example. So we have here, let's go from here. We have empty manifold, right? And we have this 2-dimensional cobordism from empty manifold to circle, right? This is not a type of 3-dimensional manifold. This is like a 2-dimensional TQFT structure. Like for 2-dimensional TQFT, objects are circles and cobordisms are surfaces. In this case, empty manifold is kind of again, instead of 2 manifold, we can consider it as a 1 manifold, and this cobordism, this disk is a cobordism from this empty 2 manifold to empty 1 manifold to this. And then in this case, this is the image of this under the extended TQFT is going to be this. Similarly, this cobordism under the extended TQFT is going to be this one. And then similarly for this red one, we have one morphism. These are one morphism. Here are the objects in the category, in the 2 category. Here are one morphisms. In a way that composition of these one morphisms is going to be just, right? This whole composition is going to be Z sigma 1 that we had before. Okay? And now, then this was the kind of first layer of extended TQFT. What is the next layer? Now, so far we looked at surface and its transversal cuttings. How about we go into 3D case, right, in here? So we have now 3-dimensional manifolds, right, which are cobordisms from between cobordisms. This orange part, right, this is a cobordism from this disk, but this disk itself is a cobordism, which is a homomorphism. Then this region is going to be cobordism between a cobordism, which is itself 3-dimensional cobordism between 2-dimensional cobordisms. It's a 2-morphism. In the same way, this one. This part is 2-dimensional cobordism, another 2-dimensional cobordism, and their kind of targets and sources of this 2-dimensional cobordisms agree. And then we consider three-dimensional cobordism between these cobordisms. So this is the red part, and the yellow part the same way. So cobordism between cobordism and the purple one is the same way, and similarly for these regions. But in the image, what it's going to give? So this is the cobordism between two-dimensional cobordism. It's algebraic data. It's a one morphism in the image category, two category, and this is one morphism in image category again associated with this cobordism. Now, this region, three-dimensional cobordism between cobordism, is going to be right between these two homomorphisms. It's going to be a morphism between them. Right? And now one can, and then in the same way, one can generalize this whole theory to this part everywhere, right? In the same manner. Everywhere we generalize it the same manner. Then we have this all these color-coded things that you can check, or I don't know. I put also labels on them, on the surfaces and cobordism between them. So you can consider, you can compose this two morphism in this way with this one and this one with this in one, and compose these two compositions, and the result is going to be, right, V prime. This whole composition, right, this three composition of four morphisms, in any way you do, it's kind of isomorphic. We should say isomorphic, not the same. Okay? And the same way, this is kind of isomorphic. This composition is isomorphic to just this one. Okay? Because in the category of, when we do higher categories, whenever we have, in this case, sorry, this is going to be equal, because in this case, we just consider up to diffeomorphism. I will give more details. But in this case, in the level of homomorphisms, they're going to be just isomorphic. And similar way, you can compose this like maybe first like this, and then like this, and then like this. But the result is going to be isomorphic to, oops, it should be algebraic part, so we need to put this. Well, these arrows, right? These arrows are in the target category, right? Our target 2 category. So their composition is going to be image of whatever the quantum invariant quantum data we assign to this part, which is variable prime. Or you can do other compositions, but it's going to be the same. Or instead of doing this, like this, these were the case, that's I'm trying to show that how we can recover from extended to non-extended one. One can cover from extended one to non-extended in this way. But also one can do more when you have extended. You can just compose this red one with orange one, right? This composition is going to be two morphism from whose source is this one morphism, whose target is this two morphism. And one can compose similarly. We can do first these vertical compositions, and then when we get 4 of these vertical compositions from this way in algebraic category, in the 2 category, then we can just compose them, and then we get eventually Z V, okay, which is some number. Well, not number in this case, which is again an element from C of Z sigma 1 to Z sigma 2. I hope this makes sense. But in the this is non-extended case, but if we have, let's say, this is a 2 category, okay, then this is going to be 2 morphisms. Because Z one is a one morphism, this is another morphism between empty manifolds, right? This is from this morphism, and in this case, in the extended category, Z sigma I, right, for 1, 2, 3, is an one morphism between D from empty manifold to empty manifold. Empty is a one-dimensional, right? If you look at this or this one or this one, they are cobordisms from empty manifolds, right? So if these are not empty manifolds but circles, what do we get? Or unions of circles, then this indicates that in extended TQFT, also this part also itself indicates I don't know how good my picture is. One can do better visuals, but one should get in the extended TQFTs with manifold with corners, right? This part has this part and this part. So if we didn't have boundary in here, if we have not empty boundary but non-trivial boundary, we had circle. This is going to be boundary which has this interior part and this part. So it was going to be a precisely a manifold with corners. So in this case, instead of manifolds, we get manifolds as a cobordism with corners. Okay. Well, let's do quickly a little bit formalization of this thing. And once extended 3D-dimensional TQFT is a symmetric monoidal 2 functor, okay, from this symmetric monoidal 2 category of bordisms, okay, whose objects are closed-oriented one-manifolds, whose one-morphisms are oriented cobordism between one-manifolds. So these are 2D cobordisms, okay, and whose two morphisms are or cobordisms between cobordisms, which are right 3D cobordisms. But the point is again in this case we do not mode out by diffeomorphisms because they are considered up to already equivalences of two morphisms. But at the top level we need to consider manifolds with corners up to diffeomorphisms relative to their boundary to make this composition is well defined on the top level. So this is definition of a category, and D is some arbitrary algebraic two symmetric monoidal two category. Okay, one can consider, for example, algebras whose objects are K algebras, one modules are bimodules, and two modules are bimodule maps. That's one candidate. And the monoidal product is again tensor product over K. Okay. Well, an example of such a TQFT is Witten-Wechselian triad. So what does that mean? Witten-Wechselian triad TQFT is a TQFT, not extended, but it has a structure that it can be extended to circles. Okay. And this has been studied by four author papers like Bartlett, Douglas, Schirmer, Priest, and Vickery. So here I want to say something. When I put an underline of somebody, this is a one person's name. I want to emphasize that by doing this underlining. Bartlett, Douglas, Schirmer, Priest, and Vickery, they proved that they classified this one extended three-dimensional TQFTs. Those once extended TQFTs taking values in Cauchy complete linear categories. They are kind of some certain nicer versions of finite tensor categories, maybe, that one can study TQFTs. These are classified by modular tensor categories, which is not something that we didn't know, right? We know that when Witten-Wechselian triad TQFT was constructed by modular tensor category. So without adding any more structure, one can extend it to a circle. Right? And their theorem can be this classification is equivalence class of such TQFTs. That means such TQFTs up to monoidal 2 transformation is in bijection with equivalence classes of monoidal tensor categories. And how does this bijection is given? We take such a functor, okay, board 3, 2, 1, 2 vect. Oops, not vect. There's Cauchy complete linear categories. Okay, D2 category. And where does the modular tensor category? It is associated with the circle. Image of circle is going to be modular tensor category. That's the idea. Okay. Okay, now we extend it to from surfaces to points. Okay, in the case of surfaces, there was no extension, it's just a TQFT. And we learned this idea of extended TQFTs, cutting along higher dimensional manifolds. And then in this picture, one can say, what stops us cutting along another direction, right? We cut along this direction let's say, XY plane, we cut along YZ plane, why don't we cut along another direction? In the sense like, for example, this direction, right? So if we cut along this direction, then what do we get? We get some, right? We get some points as well, right? And we're going to get, again, manifolds with corners, right? Now we get not only surfaces, but manifold with corners in the 2D case, and zero dimensional manifolds. Okay? If we cut along another direction, transversal direction to the previous two, then we get codimension 3 manifolds, which are just zero dimensional manifolds, which are just points. Okay? And in this case, whenever we have an TQFT and we do this extension along cutting along transversal direction in different ways, if we do n different directions, which are all transversal to each other, then we get manifolds, like we get zero dimensional manifolds. That's the corners, maximal corners. We get all the dimensional manifolds between n and 0. And in the case of 3, we get this three extended TQFT, like, or in this case, another word is twice extended or two extended 3D TQFT. And this is another name for this is fully extended. A fully extended TQFT is the one that is extended up to 0. And there are, in this case, this is going to, as fully extended 3D TQFT is a symmetric model of 3 functor from this 3 category to another 3 category. And what is this 3 category, which you can expect maybe from the previous one? Okay, objects are compact oriented 0 manifolds. Okay. And what are morphism between them? What manifolds? Okay, in this picture. Oops. In this picture, this is the objects, right? So this is like this what we have. So this is the cobordism between it. So it's a one morphism. Okay, these two objects are objects, and this line, like these are oriented plus and plus, and this line is oriented in this way. It's a cobordism between them, and the two morphism between two such things, like this one and this one, is going to be this one. Okay, this is another one morphism at the same source and target. Then two morphism between these two things is going to be this all upper piece, right? Oops. Sorry. All the upper piece between, like half cylinder between them is a two morphism. Okay, what is a three morphism between such things? If you do same things in here, all right. If you do same thing in here, let's choose another color. If you do same things in here, we have one morphism, we have another one morphism. Okay. We have this two morphism, and we have this lower two morphism between these two, right? And the three morphism between these three things is this red shaded part. Okay. That's really like, that's really visual. So you can see how much data it puts in. And the same way, we should have this much of data, extra data. The more we do the extension, the more data we put in, which a priori means the more computational ways of doing it. Because when we cut along codimension 1 manifold, we simplify our manifold. Whatever we get, lower dimensional manifolds are kind of simpler. As long as we understand their images in some appropriate algebraic category, one can recover the whole TQFT. That's kind of an idea. Maybe it's not super practical, but this is the idea. Okay. And then again, one morphism is oriented one-dimensional cobordism. Two morphism is a cobordism between those things, and three morphisms are cobordism between those things, which I forget again here. And the last morphisms are considered diffeomorphisms, real boundary. At the last one, to define compositions well and all other things, because they are not considered up to another level of cobordisms. There's not of a weakening of this thing. That's why we need to cut by saying we consider the stop morphisms up to the diffeomorphism real boundary. Okay, and this is not specific to, I should mention, this is not specific to and the three-dimensional manifolds. This extended TQFTs are more general. They're more general in animation TQFTs. And the cobordism hypothesis by which are stated, conjectured by Bayes and Dolan, and proven by Lurie, and in different approach factorization algebra homology case, it's proven by Ayala and Francis. It states that a fully extended frame TQFT, okay, not oriented one. So far, we have talked only oriented TQFTs, all manifolds are oriented and oriented cobordism, whatever, but fully extended frame TQFTs is determined by value on a point. Okay, this is very, very little bit philosophical, maybe a little bit more. In the physics case, you may say all this data of a disk, maybe physical data, this is maybe, I don't know this much, but we'll call it the principle, I guess. Maybe this is the encoding idea of this hypothesis, but I don't. Maybe factorization algebra is way better for understanding those things. And the fully extended ticket is determined by image of a point, of course, with the fully dualizable data. And whenever you have this fully dualizable object in the target category, then you can construct the whole TQFT. There's kind of classification between fully extended frame TQFTs and fully extended and fully dualizable objects in the target category. So what does framed means? Framed means manifolds whose tangent bundle can be trivialized. And then we have this like codimensional manifolds. They are stable normal bundles in the manifold. They're all stabilized. That means there exists some trivializations of this bundle into larger manifolds. These trivializations are frame things. They are key. This frame things kind of corresponds in the algebraic sense to dual, the word dual. This is like kind of correspondence. This is in the topological categories, like having a framing, like changing the framing is kind of like a dual. And in algebra world, it becomes a dual of an object. Okay. Which we have seen last lecture when I talk about properties of TQFTs is like TQFT is a pivotal functor. Non-extended TQFT is a pivotal functor. That means there's a duality data in the category. That duality data in the cobordism category is reflected on the algebraic category to be a pivotal. Okay, pivotal category. That's kind of generalization of this picture to higher dimensions of higher codimension cobordisms. And another theorem, and Lurie generalized this cobordisms from framed TQFTs, which are kind of harder to understand, framed manifolds and harder to find maybe, to any kind of TQFTs by using homotopy fixed points, not only dualizable objects from homotopy fixed points. So one can like Lurie use infinite category language and homotopy fixed point language in the category like algebraic target case, like fully extended oriented in the case of, for our interest in these lectures, we just considered oriented TQFTs, oriented manifolds. In this formulation, a fully extended three-dimensional oriented TQFT is in bijection with homotopy SO3 fixed points in the target category. So a target category is kind of an infinity 3 category, which is an underlying infinity group point, which is a space. And on this space, there's an SO3 action. And then this SO3 action has homotopy fixed points. And whatever those up to equivalence are the corresponding isomorphism class of oriented, fully extended TQFTs. And there are studies, there are works on this area as well. And what is the algebraic, like when we study such things, what are the target category one can ask? What is the, like, what do we replace vect? Okay. A natural replacement for vect from non-extended case to 3 extended case is this TC, the category of tensor categories, whose objects are finite rigid monoidal categories. And morphisms are finite bimodules, okay, over these monoidal categories. And 2 morphisms are bimodule functors, and 3 morphisms are bimodule transformations. So this is a 3 category is in some sense that's very complicated maybe to understand. Is objects of this category are certain linear categories. And sorry, this is yes. And there's a and the theory of Dr. Schumer, Priest, and Snyder. They say fully dualizable objects in TC. Remember, they correspond to fully extended framed 3D TQFTs. Okay, they are in bijection with fusion categories of non-zero dimension. And similarly, they compute the homotopy fixed points in this 3 category. And there are spherical fusion categories. And the kind of the most natural candidate for these things you may come up with immediately are state sum TQFTs. So it's conjectured that like state sum TQFT extends to point, and it's kind of also proved. I should have mentioned there's a kind of extension of work of Bakalov and Krylov. They kind of stated this and kind of proved this in some sense. Structure by okay, this is kind of the first extension. This was the kind of first perspective. It was extended TQFTs. I guess it's a very good story. Why one considers this like cutting along higher codimensional manifolds and getting more different structures, and there are studies on this thing. Maybe we can give a break of 10 minutes and then continue with remaining 2-3 more different generalizations of these TQFTs. Okay, next generalization is TQFTs with defects. And defects are, this is in some senses similar to extended TQFTs, but there are kind of important differences between them. Instead of using, uh, cutting along higher manifolds with corners, this one uses some chosen stratified subspace of the cobordism. And this chosen stratified subspaces has like maybe boundary walls or something. They're also attributed some physical meaning, which I'm not familiar, I don't know. And then, and there's there's again a morphism algebraic data between these stratified subspaces. So in short, or kind of a slogan, defects are kind of lower dimensional submanifolds of the cobordisms that carry non-trivial topological or physical information. And as of more formally, more precisely, a three-dimensional defect TQFT is a symmetric monoidal functor, like cobordism 3 to defect D to category vector spaces. As you can see, this one now is again one category. And here again, that means this is kind of one category. But in this category, there are some special morphisms given by relating to two different parts given by this data D, defects D. In this case, similar to non-defect TQFT, objects are oriented closed surfaces, and morphisms are oriented cobordisms, which are endowed with a stratification by submanifolds labeled with elements of a fixed labeling data. So, and they are subject to certain algebraic relations given by D. So it's like we have again some cobordism, three-dimensional cobordisms, and maybe we cut along this one, but there may be here, there may be some stratified some subspace in here, which divides this region into like this part into two, which divides W, and W is whole, and this part is W prime, this is W, okay? And then this is element of D, maybe, okay? And this defect has some as is like it is not arbitrary data or something. It's like whatever algebraic data assigns in here, coming from whatever algebraic data is coming from here, this D has some data that relates them. Okay, and want to have maybe this different stratified spaces for above. Okay, and then they're related in this way coherently. like this composition this way correspond to the nicely given this data of a D. Well, in some sense, this is not like cutting along codimension one submanifolds, or like it's like putting like extended TQFT is more unified and like more how to say, it's more unified in that sense. Also, it's more complicated submanifolds with corners. But in this one can also choose complex defects. But this is like once introduced defects kind of as desired, maybe. I'm not expert on this. And then one gets extra data with conditions on this extra defects data from the conversion category. And Car Karkuval and Mausberger and Schaumann, they proved that any three-dimensional defect TQFT, they needs a K-linear grade 3 category with tools. Again, this whole thing that this image of this data of D in the target category can be collected into a 3 category. And there is, in this case, there's another rich graphical calculus as well, like 3 categorical way, which is a really nice rich theory. And the surgery TQFT that we know, right, can be generalized, is generalized to defect TQFT by Karkuval, Runkel, and Schaumann. And again, state sum TQFT is generalized to defect TQFT recently by like 2 years ago, and Musberger. And these are very rich theories. They again, the results, okay, the structure, maybe the definition does not involve higher categories, but the results kind of really higher categorical ideas. And there are way more papers and studies in these things I should have put, but due to maybe Lyme limitation, also I'm not very expert on this field, and my knowledge is limited. Very rich and active area of study. You can look at our survey paper there. We put more references on this defect TQFTs. And next, I will talk about homotopy QFTs, which is kind of my specialty, which I studied in my thesis as a like homotopy QFT. In my thesis, I kind of studied homotopy QFTs plus extended TQFTs in dimension 2. And later, I worked we worked with Alexis Virelizier on certain generalizations of uh, this things. This homotopy QFTs, which I will talk hopefully. Like, what is homotopy quantum field theory? We change from T to H. What does this homotopy says? What is a homotopy? To have a homotopy, we need to have maps. And in fact, homotopy quantum field theories are what is the slogan? Is like TQFTs involves manifolds and cobordisms, and HQFTs generalize this picture between manifolds and cobordisms. It generalizes it by fixing a space and having a continuous maps to that. Okay, like it adds more data to this category. It doesn't care about cutting along higher dimensional manifolds. It's the total different perspective of looking at TQFT. The two previous ones, like the first one is cutting along codimensional one submanifolds. The second one is like decorating the cobordism category with some useful, maybe physical and maybe non-physical algebraic data coherently and study them. Some extension again of the usual together. But in this way, we say, okay, we take a cobordism category. What we do, instead of just studying manifolds and cobordism between them, let's fix one target category, some topological space which is connected and appointed, and let's consider just continuous maps from the surfaces and continuous maps from the cobordisms, and then let's assign some topological or quantum data to those things. Okay, how does it generalize to TQFTs? I will talk more in this. How does it generalize to TQFTs? It generalizes in the sense if this homotopy, if this continuous maps are constant, just constant maps, no data, then it reduces to TQFT. Okay. TQFT is like manifolds equipped with trivial maps to some target space, just constant maps. And then instead of constant maps, if like that's a TQFT, but we never, if there's a constant map and no data, we throw them away, which we don't do. But if we have trivial maps and then we consider what happens if the maps are not trivial, if they are more general, that brings us more structure. And you may say, well, who cares fixing a target space and studying continuous maps or homotopy classes of maps? Well, some people care because this target space can be classifying space of a principal bundle. And then homotopy classes of maps to classifying space is in bijection with principal bundles over the manifolds that you started with. So if you assign a numerical invariance to these maps, this continuous map, using this homotopic quantum field, and if you can distinguish non-homotopic maps, that's the potential feature of this homotopic QFTs. And if the target is classifying space of some structure, whatever, like principal bundle, then you can distinguish these structures on your manifold, these principal bundle structures. Okay? Like TQFT is like distinguishing manifolds from themselves, some manifold invariants. Homotopic QFT in some examples, just maybe special examples, in the case target space is a classifying space, can be considered as like distinguishing different structures on your manifold. Because these structures, isomorphism class of these structures on your manifold maybe, are in bijection with homotopic classes of maps to this certain certain classifying space. Let's go more detail, more precise definition of homotopic QFT. We fix a connected pointed CW complex. There's some one fixed point which is connected. And a three-dimensional homotopic quantum field theory with target X is a symmetric modular function from this XCOP3. Okay. So what is this XCOP3? Okay. Those objects in this case, to be more precise, pointed, okay, surfaces, pointed oriented surfaces. So closed, we need to add. And morphisms. This is not just normal one category. There's only objects and morphisms are there is in the case of morphism, cobordism doesn't have points. Oops, I forget the most important thing. Plus a continuous map, pointed map from like sigma to x. Okay, the sigma is pointed with little sigma. There's a fixed point, and the target space has a fixed point, and we have a continuous map. In particular, you can observe that the objects of this category is way more than COP3. So COP3 sits inside XCOP3 by just considering constant maps. Constant maps. It takes everything from sigma to little x. Okay? So it's a way more larger category a priori. And morphisms are like cobordisms or oriented. Three-dimensional cobordism between surfaces equipped with in this case not a continuous map, but homotopic class of maps. And we consider up to the diffeomorphism real boundary. Okay, in this case, there's one more condition. If we have a cobordism, okay, this is again, let's consider sigma 1, sigma 2, this is W. Okay, now we fix some maybe space X at a point, and we have surfaces here, and this surfaces has points, sigma 2, and we have map, this is F1, this is F2, right? And F1, like the object, what do we have? And here we have a homotopic class. Okay, it's not a little f1 and f2 are just continuous maps, but f itself is homotopic class whose restriction to this boundary is going to be equal to f1, whose restriction to this boundary is going to be equal to f2. It's a homotopy class of maps restricting this given maps on the boundary. So this tuple, so W and F equals class of a map. And we, of course, W is also considered up to diffeomorphism. Implicitly, I don't denote that. This is also equals class, in fact, of up to diffeomorphism boundary. This is an element in form X corp 3 from sigma 1, sigma 1, right? F1. This is one object, this data. And the other object data is sigma 2, little sigma 2, F2. Okay? And these are continuous maps. These are constraints. This is a homotopy class. Okay? And the point and the condition that we put is this restriction of this on the boundaries is F1 on the F2 corresponding boundaries. Okay? Again, this is maybe read last one more time. Oriented closed surface endowed with a map, continuous map to X, and oriented cobordisms equipped with a homotopy class of maps to X, which restricts the given maps on the boundaries. Shortly. Well, in particular, so if we draw it again, now without boundary, if we have a three manifold is boundary is empty. Let's say closed oriented three manifold, we have orientation. Okay. And I don't know, there may be some essential spheres, there may be some surfaces behind, we don't know, it's a three-dimensional manifold, but it doesn't have boundary. So it's a cobordism from empty manifold to empty manifold. An empty manifold has this, we have fixed this target space, maybe this target space we fix X point. Empty manifold has vacuous empty map, in this case, pointed map. But since there's a cobordism, this is equipped with what? Some homotopy class, where F is a homotopy class from M. This is not pointed because remember, cobordisms are not pointed, just surfaces are pointed. There's no point. Homotopy classes of maps from this M to X. So when we apply such a functor Z, what do we get? Z empty manifold is again it's monoidal. It's going to be K. Again, here it's going to be K. Going from bottom to top. So, and Z of, right? This is Z of M F, right? Which is determined at the image of one, because any linear map from between two rank one vector spaces, linearity implies it is determined by the image of one. Okay, one of K. And this Q is the invariant of this homotopy class. And that's what I want to say in here. A three-dimensional TQFT is a produces scalar homotopy invariant of maps. It assigns a numerical invariant to not manifolds. In the case of TQFTs, it was it. So we assign numerical invariants to manifold. Now we equip manifolds with continuous maps, and in the top dimensional manifolds in a Bordism category with homotopy classes of maps. So the numerical invariant becomes in TQFTs becomes a numerical invariant of a homotopy class from this manifold to fixed target space. So in short, maybe I should say TQFTs produces numerical invariants of closed oriented three manifolds, and three-dimensional HQFT produces homotopy classes of maps. Okay, and one can consider if this homotopy class, one can consider every TQFT can be considered as HQFT. Well, HQFT is a generalization of TQFT. Whenever we have an HQFT, such a functor, if we restrict ourselves to constant homotopy class, that's the invariant of the manifold. Okay? If F is constant, if F does not have any information, okay, we just restrict those constant maps, we get a TQFT. Whenever you have an HQFT, there is this data of an HQFT sitting there. TQFT is sitting there. It's a trivial data, trivial extra data. In that sense, HQFT generalizes TQFTs. Okay? This embedding in the algebraic level, this is like constant maps, constant data. Okay, and common example, a straightforward example. One may ask, is there exist? Okay, we can formulate this theory, but is there exist the example? non-trivial example, and it exists. Whenever we take third cohomology of the target space, third cohomology class, then we form a cohomological HQFT, which takes any homotopy class. This is the manifold from empty to empty, so it's closed through manifold. For any homotopy class, its image under this TQFT is the evaluation of the pullback of this third cohomology, which is now at, right? The pullback is in a third cohomology of M with K star. But we have a fundamental class of M lying in third homology. And then if you pair them up, right? And then this is a number, and this number is the invariant. This is kind of integrating fundamental class over the pullback homotopy class, pullback cohomology class. Okay. And now, what there is general, like this, one can study this HQFTs by putting some order or like some kind of filter on the target space, and these filters are given by that in our consideration of consideration of maybe triviality and triviality and my work is like as being a type, being n type. What is a topological space means that n type? It means that it's all higher homotopy groups above n, they vanishes. Okay, just remember this is the homotopy classes of maps from ith sphere to X. They form a group. This is the ith homotopy group of the space. If they vanish for all i's larger than n, it's just homotopy data of lower than n dimension case, then we call this such spaces as homotopy n type. They don't have higher homotopy data. They're trivialized. So what is the n equals 0 case? A connected 0 type, right? It means all homotopy groups vanishes. Also 0 case, connected means it's 0. That means it's just a pointer like contractible topological space. And this is a kind of where does this whole generalization coming from? And whenever you have a continuous map to contractible space, it is homotopic to constant map. So that means HQFT with connected 0 type target is precisely equivalent to TQFT. Okay. And then what is the next level? One can take n equals 1. And when we take n equals 1, then what is a connected 1 type? That means pi 2 and above, they're all vanishes. There's only the fact that it's connected, there's no pi 0. And we have only pi 1. And pi 1 is just a group. We have only one group data, and that's a G. That is by definition, it's called dynamic McMaster space of type KG1. And such a space is classified space BG, where G is the fundamental group of this group. G is precisely pi 1 of X. And in this case, in fact, all of the theory that we have seen in the first three lectures is extended to homotopy field theories, homotopy quantum field theories. The first one, any spherical G fusion category, you need to notice that there's a notion of G fusion category. I didn't define that. Means there's a grading on objects. Okay, there's a fusion category, and then there's a G fusion category. That means there's a special grading on the objects which behaves multiplicatively under monoidal product. If you take tensor categories of these gradings, they lie in the product, or like if you take then we have C, which is kind of union of G is in G, CG, okay? Direct sum of category pieces. If we take object V in CG and V prime in CG prime, V tensor V prime is going to lie in CG G prime. The monoidal product takes the group product structure, or it either lies in here or it's a direct summand of some elements in here. And if given such a category, spherical G fusion category of non-zero dimension, one can construct a state sum TQFT with target classifying space BG, and trivialize generalize all the state sum formulation to homotopy field theories equipped with maps. Okay, and the same methods, the generalization of similar methods. In the same way, they generalized surgery method. There's a similar G-graded version of modular category, And any such category give rise to a surgery HQFT with target B. And moreover, this center construction in both algebraic level, there's this notion of graded center or G center. Okay, G center of a G graded categories. There's such a formulation, and that construction makes the connection between state sum HQFT with target BG and surgery TQFT with target BG. So Troyer and Viralizier, they completed this program of this whole what is known for TQFTs for the case of HQFTs. And another consideration is that I told you, like whenever we have an HQFT, there is an underlying TQFT, which is kind of boring. They come from just looking at constant maps. But there's a more interesting way of taking kind of average of doing these things. If your group is like finite, if in this examples that we have like BG case or homological case, if group is G is finite, then this HQFT goes into TQFT. There's this orbifold construction by Schweigert and Voigt. They take HQFT and creates an interesting TQFT. And one example of this is like taking homological HQFT, which takes a third cohomology class, right? From this, they derive a Dijkgraaf-Witten, well-known TQFT. Dijkgraaf-Witten TQFT is an example. And now we covered what? Connected zero types, connected one types, and next question, once we all know results on one types, they're all generalized. Next question, connected two types. Well, in the connected two type, it means a topological space which has only non-trivial data. It's a connected, zero cases trivial, pi1 and pi2, and some extra first K invariant. So it has only two groups data of non-trivial homotopy groups, but this has been studied in different algebraic structures, and one of them is cross-module. Cross-modules model algebraically these two types, connected two types. And whenever we have a cross-module, that means a group homomorphism. So E and H are groups, H acting on E, and this map is equivariant. There is a kind of corresponding, there's a classifying space, BG, B chi, okay? It's a topological space. And it is connected to type. Okay. So what do we know? Its fundamental group is the co-kernel of chi. Okay, and its kernel is its pi2 is kernel of chi. There is this relationship between this algebraic structure and the corresponding two-type The co-kernel of this algebraic gadget is the pi1 of the resulting manifold, this construction, classifying space construction. And the kernel of this map is the pi2 of this classifying space construction, the manifold. And with Alexis Viralizier, we generalized state sum construction to connect to two-type case. So whenever we are given a chi fusion category, let's say chi we are cross module from E to H, that means we have space B chi, which is a two-type, which is connected two-type, whose pi1 is co-kernel of this chi, whose pi2 is kernel of chi. And then whenever we are given a spherical chi fusion category, then we get a state sum TQFT. Which gives a three-dimensional I should specify state sum HQFT, which uses the similar skeletons, but we add way more data there. We add the homotopic, the data of homotopic classes are added carefully, and we check more invariance under all these possible homotopies. Okay. The methods are similar, but there is an extra data and which brings extra relations that they all needs to be checked. Okay, but in this case, what is a chi fusion category? Remember, G fusion category is a category is a kind of fusion category where objects are graded by G and the tensor product of G of the components like we have like product in the group. In this case, this is way more general. In the first level, objects are graded by target of this map H, and their tensor products of the component elements are again related by group structure on here. But at the same time, now morphism spaces for each fixed two objects are E-graded, right? And then and then you need to ask, well, morphism spaces are more complicated because there's a composition structure there. Okay, when do we grade? What does happen if, because we can take composition of morphisms and tensor product of morphisms. There are two relations. So if you take two different degree of E of compositions, the composable maps, their composition is going to be from their group product. They're going to line their group product line, right? Like X, let's say Y and Z. Let's say this is F and G. And this has grade E in E, okay? And this has grade E prime in E. And this has grade H1, this has grade H2, this has grade H3. Okay. First of all, there's a relationship between these two things, and that relationship is the following. H2 is equal chi E times H1. Okay. That's where does this map comes into play. The degree of the target is taking the H1 degree of the source and multiply by the image of this grading of the map. Okay? This shows how much one needs to transfer between different components. It is given by chi, and this really reflects something topological. There's a topological idea in it, and similarly, H3 equals H2, sorry, chi E prime H2. Okay? And then now when we consider this composition, this has degree H1, this is degree H3, then we have G composition F. The G composition F, it has degree E prime, okay, in E. Okay. And similarly, as in the G grade categories, X tensor Y has grade, H grade is H1 cross H2. And Y tensor Y is grade H2 tensor H3. And one can have, again, now one can take F tensor G, okay, if this is, okay, let's also explain this. This is one thing, how the E graded things are related. But if we have F, okay, from this again X to Y and G, graphical calculus notation, let's say B to T, okay? And let's say X H grade H1, Y has grade H2, V has H grading H3, and T has H grading H4. Okay? And let's say F is graded by E and G is graded by E prime again in E. Okay? So the question is, what is the grading of F tensor G? Which is, remember what we do, F tensor G, and it's come from X tensor V to Y tensor T, right? And we know that this has, right, from this case, we know that X tensor Y, sorry, X tensor V has grading H1 cross H3. And Y tensor T has grading H2 tensor H4. Okay? And you may say immediately, okay, this must be have grading E times E prime. But it doesn't work. That doesn't work because of, I didn't give you, the reason is that it doesn't work in the sense of this axiom fails. It is, if it was, so what is the axiom? If it was, let's say, another color, let's say if it is A prime, then we need to have H2 times H4 is chi E prime times H1 H3. When you study cross-module actions, this is not always true. So what is the right definition? The right definition is this is E times, okay, H1 act on E prime. Okay. Remember, I said when I introduced, I didn't tell you definition of cross-module completely. I just said this is a group, this is a group, this is a group homomorphism, but it's an equivariant one in the sense that H acts on E, and H acts on itself by conjugation. So the action of H on E, that is denoted by like H1 acting on E prime. Okay? When you do this, then it works. There is Pfeiffer equation that one employs, and then in that case, this is precisely equal to that one. So it's satisfied. This is like there are two compositions for there are two operations for morphisms in a category, not two categories. We are just having a normal category. For objects, when you have a monoid category, you can take product. So there is one kind of operation that you can do for different objects. But in a monoid category, when you have morphisms, if they're composable, you can compose. That's one object. But if they're not composable, you can anyway you can take the tensor product. So this E and H gradings must match in each possible things. If they're composable, they again multiplicative. If they're tensor product, they're kind of twisted product for you. And then one generalizes this whole this is kind of a notion of a chi-graded category. So, and then one needs to study what is chi-pivotal, what is chi-fusion, what is chi-spherical, uh, all these, and then standard generalizations in some sense that we study in another paper. And then we study Hopf-Chi coalgebras and their representations. Where do they come from? There are non-trivial examples of these things, capture different homotopy classes, in fact. They're not trivial invariants of maps. They distinguish some different homotopy classes of maps. So this is what I want to say shortly, that the state sum construction extends to this two type case. Okay, and our plan is to go with we are asking now, how about the surgery case? How about the chi-center construction? Like the way that it's like the going from HQF, like zero type is precisely TQFT, and one type is studied and has been figured out in all the program that I mentioned to you the first 3 lectures. But going from zero case to like zero type to one type and one type to two type, I can say one type to two type, there's way more intricate algebraic data than introducing a one group. Like here, like in this level of complexity, there's only one group. In the case of going from 1 to 2, there is another group involved and there's an action involved. Everything needs to be checked. So everything that is checked on the algebraic level, generalization, and topological level of generalization, the complexity a little bit increasing. But we hope that the whole program works for these chi-fusion cases, connected two-type case. Okay, lastly, I want to talk a little bit about non-semi-simple quantum invariants, which are a very active area of research. They're very interesting things, and then there are very interesting results. Again, I'm not expert on this field, but I want to give a short glimpse of what is going on. So there's in the late 90s finite dimensional Riemann-Hopf algebra from not a representation category, not a spherical category. It's just a sum Hopf algebra with Riemann structure. Okay? Hennings formulated the first non-semi-simple quantum invariant of a closed manifold. This is not like there's no categorical data, just Hopf algebra. But then using graphical things from the Hopf algebra data, Hennings provided non-semi-simple quantum invariants. Okay? And it generalizes the Witten-Wechselian triad in the following sense. If we add semi-simplicity, okay, there is no semi-simplicity mentioned here. If this algebra is not semi-simple, then it gives this invariance. If it is semi-simple, this construction also gives invariance. But if it is semi-simple, it reduces the Witten-Wechselian triad invariance, surgery invariance, but not from, well, you ask immediately this invariant, right? Like Hennings defined coming from just Hopf algebra, and Hopf algebra is not a fusion category, right? But if you have finite dimensional ribbon semisimple Hopf algebra, its representation category is modular category. And from this modular category, you can get the written Rashid triangle. And that invariant is precisely exactly in the semisimple case the Henning's invariant that is they coincide. So this is kind of more general than within Rashid triad, non-semisimple case. And then Lubashenko generalized Henning's construction to kind of categorical language using ribbon finite tensor categories. But this has some subtleties in the sense that when you take disjoint union of manifolds, okay, when you try to extend this a numerical invariant to closed manifolds, and as I said to you before, you try to say, okay, let's try to extend this. You can extend in a composition way as a category, but you cannot extend in a monoidal product. When you take disjoint union of manifolds, when you look at the invariants, they don't multiply all the time. Okay, especially those things with first beta numbers and non-trivial, there's a problem. But Kerler and Lubushenko showed that this is not a quite TQFT, but there's a kind of extended TQFT structure in it. And then in the kind of last 15 years, maybe there's a lot of work on this, this completing the TQFT from semi-simple cases. Because when you have a TQFT, for example, other than numerical invariants, you also have, for example, representations of mapping class groups, which give some information about symmetries of the surfaces itself. So TQFT has more structure. So there's a question of how can we extend these non-semi-simple invariants to TQFT case with some of them. And then along this way, one of the key tool in this construction of non-semi-simple TQFTs is what is called modified trace. And this is introduced and studied by Gier, Potroy-Mirand, and Realizier. And using this, Constantino, Gier, and Potroy-Mirand, they constructed non-semi-simple surgery quantum invariants. Okay, this is again not a TQFT, just a numerical invariance. Okay, but then in Berenzi, in his thesis, he provided a once extended TQFT formulation. This with quite a bit of precise decorations on the surfaces, on the manifolds, like once extended TQFT formulation in the non-semi-simple quantum invariants. Okay? And another way, Hennings is the first one getting this non-semi-simple invariants, but there's another construction of Kuperberg using Higart diagram decomposition. Higart decomposition or Higart splittings of three manifolds, closed three manifolds. One can write every closed three manifold as some combinatorial data on some closed genus G surface, gluing two handle bodies. Okay, because a handle body means it's a three manifold whose boundary is a genus G surface. And then if you glue, and for any manifold can be obtained like this. And then Kuperberg using this certain decorations of these Higart diagrams using the data of a finite dimensional non-involutory Hopf algebra or involutory. Okay, he got non-semi-simple quantum invariants of three manifolds. But if this becomes involutory or semi-simple, if you assume this Hopf algebra is semi-simple, similar to Henning's case, then the invariant corresponds to Trier-Viro Barrett-Westbury state sum invariant of the representation category. Again, these invariants are coming from Hopf algebra, not from certain fusion categories or modular categories. But the representation category, when they're semi-simple, they are going to be spherical fusion category. And then one can associate the corresponding invariant. And this diagram kind of commutes in the sense. But whenever we have such thing, we have center construction as well, right? Whenever we have semi-simple thing, in the semi-simple case, this VRT invariant of the instead of center, there's one should ask the center of this representation category, we know is some modular tensor category, but that modular tensor category is the representation category of the Dirichlet double of the Hopf algebra. There's kind of doing things at the Hopf algebra level, right? Like Hennings and Kuperberg, and then or getting taking the representation categories and doing things in the fusion category level, modular tensor category. But center construction kind of relates all this construction in a way, in the semi-simple case. Okay? And Chang and Kui extend this relationship in the semi-simple case to the non-semi-simple context. Okay? Okay, like we had all this relation between these constructions in this level, in the semi-simple case. Okay, these two are invariant. These these things, and then Chang and Kui, recently 2019, I guess, they extended this relationship between these two invariants to the non-semi-simple case, and Constantino, Giampatora, and Miranda Trier, they generalized this. Here they had it studied. Remember, they generalized surgery quantum invariants, and the state-sum invariants are generalized by these four authors to non-semi state-sum invariants. And further, Constantino, Giampatora, Miranda, and Veredizier, they extended these non-semi-simple invariants to non-compact three-dimensional TQFTs. That's even more generalization. Manifolds are not necessarily compact, and there is this generalization as well. And so this non-semi-simple invariance, like this generalization involves totally different perspective. You don't consider cobordism category at all. You don't consider cutting all of higher dimensional submanifolds. You don't consider adding more structures. You don't consider adding some maps, whatever. You say we construct TQFTs from certain representation categories. And these representation categories in general come from representations of finite, not all the time, but in general, they come from representation of finite, semi-simple Hopf algebras. So the question is, okay, we figure out kind of most of the things, maybe, not everything, of course, we figure out most of the things in a semi-simple case. So can we generalize this whole this construction when we generalize the algebraic input? This is like more of a generalization on the algebraic input to capture more topological data. Okay? And I didn't have time to write down, like there's also the work on this from this non-semi-simple TQFTs to getting more data on quantum representations compared to semi-simple invariants. So this is another perspective, the Zulkes algebra case, and let's say let's weaken this condition in the algebra case and try to do all these tools in that case as well. And then there are really fruitful results, useful constructions, algebraic structures, and topological invariants. And that's all I want to say. Thank you for your attention.